balanced voltage dips in synchronous machines. So here we are considering the simplified system shown in the figure, right? So if we observe here simplified system, what is the system here? Just HV MV transformer, primary side is HV and secondary side is MV, and for that particular bus there is a synchronous generator is connected, and for that there is a load is connected. Okay, so here, so when it comes to the simplified system, so what they are saying here, synchronous generator is connected to a medium voltage bus close to the secondary side of the HVMV transformer, and during a fault, during the fault condition, the synchronous machines can be modeled as what? Voltage source behind impedance. So here voltage, how much voltage it will be experienced by the customer. Okay, so how much voltage is experienced by the end customer during the fault is found from this model, which is given as what we can write, right? UMV equal to, so UMV equal to what we can write? Z generation into UHV divided by overall resistance, that is Z generation plus ZTR. Alright, plus again, plus what we write again? Z generation into, okay, into what you should get? Into, sorry, Z generation divided by Z generation plus ZTR into UHV, it is finished. Next is ZTR into E generation divided by again overall resistance, that is Z generation plus ZTR, right? This is the UMV, voltage experienced by the end customer during the fault condition. So if we assume that back EMF of E generation of the synchronous machines is equal to 1 pu, then we get the expression during the voltage drop. So we get that 1 minus UMV. So 1 minus UMV equal to Z generation divided by Z generation plus ZTR into 1 minus UHV. So if we assume that back EMF E generation of the synchronous machines is equal to 1 pu, then we get the voltage drop experienced by the end customer is this one. Okay, so voltage experienced by the customer, right? Voltage experienced by the customer, by the end customer, in case there is no generator is connected. Okay, there is no generator connected to medium voltage, is equal to UHV, right? So when there is no generator is connected, whatever the primary side, that will be the output side. So the voltage experienced by the end customer in case there is no generator connected to medium voltage is equal to UHV. So the reduction in voltage drop, so the reduction in voltage drop is related to what? It is related to almost a impedance ratio, right? It is related to the impedance ratio between what? Between the transformer and the synchronous generator. So here the power quality experienced, because we during the fault condition and during the no generator is connected at the medium side, so the customer, the power quality experienced by the customer is instead quantified as the number of voltage dips. Okay, so how it is quantified? As number of voltage dips over a long period, that too with a residual voltage below a threshold, below a certain threshold. So that information what we get from the customer, that information to the customer, this gives the information to the customer that on the number of times per year that a device or a process is expected to trip. Okay, so that information gives the to the customer on the number of times per year that a device or a process is expected to trip. So this is about the balanced voltage dip in a synchronous machine.